Okay, let's dive in. For anyone keeping tabs on the world of large language models, and who isn't these days, instruction tuning is basically how we get these things to actually follow directions.
Right, it's become pretty standard practice.
But here's the challenge. We are just swimming, maybe drowning in data sets. So how do you pick the right stuff to train on?
It's a huge problem. Like having a massive pantry, but only needing a few key ingredients for the perfect recipe.
And what's really wild, like that Lima paper showed, is that sometimes, less is actually more. Quality over quantity.
Exactly. Lima used just 1,000 high-quality examples and got amazing results, rivaling models trained on a much, much larger data set.
Which perfectly sets the stage for today's paper.
It does. The sheer amount of instruction tuning data out there means the bottleneck isn't getting data anymore, it's picking the best data. Which brings us to MIG, automatic data selection for instruction tuning by maximizing information gain in semantic space.
Quite a title.
It is, but it gets right to the point. This paper tackles that exact problem, how to curate data smartly when you have tons of it.
So if you're out there, maybe an AI researcher, an ML engineer, and you're wrestling with this data selection headache, trying to get the best bang for your buck in terms of training data and compute time,
then this deep dive is definitely for you.
We're going to unpack a method, MIG, that promises a smarter, more efficient way to build those instruction tuning data sets. Think potentially faster training, maybe even better models.
Yeah, that's the goal. And for anyone short on time, here's the quick version, sort of the first-minute summary. MIG introduces a new way to measure how informative a data set is, looking at both the quality of examples and their semantic diversity. It does this using something called a label graph to map out how different instruction types relate to each other. Then, the MIG algorithm cleverly picks data points one by one to maximize the information gained on this graph.
And the results?
Pretty strong. MIG consistently beats other top data selection methods across different data sets and base LLMs, and maybe the headline result, it can match or even beat the performance of using a massive data set like Tulu 3 with just 5% of the data.
Wow, 5%, that's efficient.
Incredibly efficient, especially for human preference scores. The gains were significant even with that small fraction. It really points towards more streamlined LLM development.
Okay, that's a super compelling snapshot. So digging in deeper, the motivation here seems to be that older methods maybe weren't sophisticated enough.
Kind of, yeah. Many existing techniques look at quality and diversity as separate things, and their ways of measuring diversity might be a bit superficial, not really getting the underlying meaning or semantic intent, especially for complex instructions.
They might just be looking at surface features, not the core concept.
Exactly. So MIG tries to be smarter about it. The core problem they define is, you've got this big pool of data, you have a budget, maybe time, maybe compute, meaning you can only use a certain amount. How do you pick the subset that gives you the most information?
Okay, it defines the goal clearly. And what does a single data point look like in this instruction tuning world?
Good question. It's often not just one question and one answer. Usually it's a multi-turn conversation, back and forth dialogue.
Oh, natural.
Right. And crucially, each data point comes with labels like the task category, maybe the domain, stuff like that. And importantly, a quality score, some measure of how good that specific interaction is.
Got it. Multi-turn, labels, quality score. So how does MIG take all that and start measuring information diversity? You mentioned the label graph.
Yes, the label graph is fundamental. Instead of looking at data points in isolation, MIG maps out the whole semantic territory using this graph.
How does that work?
Imagine every unique label you have, task, type, domain, whatever, as a node, a point on a map.
Okay.
Then the edges, the connections between these points, show how semantically similar those labels are. The strength of the connection, the edge weight, is based on textual similarity between the labels.
Makes sense.
And to keep things manageable and focused, they use a threshold, T, to prune out the really weak connections, the ones that aren't very meaningful.
So you get this network of related concepts. How do the actual training examples, the conversations, fit to this graph?
Each data point is represented by a binary vector based on its labels. If it has a label, it's a 1 in that position, otherwise 0. Simple enough. The initial, let's call it raw, information of a data point is then linked to its quality score and how many labels it covers. High quality, lots of relevant labels means more raw information.
Seems logical.
Yeah.
But you mentioned issues like semantic overlap, annotation bias. How does the graph help with that?
Right, this is where information propagation comes in. It's a really neat idea.
Okay.
The thinking is, if two labels are semantically close connected in the graph, information from a data point linked to one label should sort of spill over or propagate to the related label.
Ah, like a ripple effect.
Exactly. They model this using a propagation matrix, let's call it A, and a hyperparameter, alpha, which basically controls how much information flows along those graph edges.
So alpha is like a tap controlling the flow.
Sort of, yeah. There's a formula, but essentially it spreads the initial information of a data point to its direct labels and its semantic neighbors on the graph. This gives you a propagated information vector for each data point.
Which gives a richer picture of what concepts it covers, not just the explicit labels.
Precisely. It captures that nuance, accounting for semantic similarity.
Okay, cool. So we have this propagated information for each data point. How do we then figure out the total information for the whole selected dataset?
They sum up the propagated information vectors for all the chosen data points, but here's the key part for balancing quality and diversity.
Play.
They apply a special function to this sum. Let's call it phi.
What's special about phi?
It's designed to be monotonically increasing but marginally diminishing, or upper convex, meaning it always goes up as you add information, but the rate of increase slows down. Think diminishing returns. The first few data points covering new areas add a lot of value, but adding more points in an already well-covered area adds less and less marginal value.
Ah, so it naturally encourages diversity by rewarding information gain in less represented areas of the semantic map.
You got it. It pushes the selection towards covering more ground semantically rather than just piling up examples in one popular category, even if they are high quality.
Okay, that's a clever way to measure dataset information. But, with potentially millions of data points, checking every possible subset to find the best one, that sounds computationally impossible.
Totally infeasible. You'd never finish calculating it.
So how do they actually do the selection?
They use a greedy approach, which sounds maybe less optimal, but it's actually very effective here.
Why does greedy work well?
Because the information measure they designed has a mathematical property called submodularity.
Submodularity. Remind us why that's helpful here.
Submodularity basically is that diminishing returns property we just talked about. Because adding a data point yields less additional gain if you already have similar information, a greedy strategy works remarkably well.
How so?
It means that if you just iteratively pick the single data point that gives you the biggest information boost at that moment, you're guaranteed to get a solution that's provably close to the true optimal solution. It makes the problem tractable.
That's crucial for making it practical.
Okay.
So walk us through the MIG sampling algorithm step by step.
Sure. It starts simple, empty selected set, then it iterates. In each step, it looks at all the data points not yet selected.
Right.
For each of those candidates, it calculates how much would my total data set information, using that phi function, increase if I added this specific point.
And it needs to do that efficiently somehow.
Yes, calculating the exact gain can be slow, so they use a gradient-based approximation, which is much faster. Then it just picks the one candidate point that offers the highest approximate information gain, adds it to the selected set, and removes it from the candidate pool.
And repeats.
And repeats that process until the selected set reaches the desired size, the budget you set.
So always grabbing the next best informational bang for your buck, guided by a label graph and that diminishing returns function. Neat. Okay, let's talk evaluation. How did they test if MIG actually works better?
They were pretty thorough. They used 3 different large data pools. First, Tulu 3, that's a big real-world instruction data set with lots of topics.
No.
Then OpenHermes 2.5, which is interesting because it mixes data from 16 different sources. And finally, Exoda, a pool focused on high-quality conversations.
Diverse test beds. And how did they measure the performance of models trained on data selected by MIG?
They used a whole battery of benchmarks. For human preference alignment, things like Alpacaival version 2, MT bench, Wild bench.
Okay, the standard one.
Yeah. And for knowledge and reasoning, they used ARC, BBH, MMLU, Human Evil for code, GSM8K for math, IFEVL for instruction following. A broad suite.
Comprehensive. And they used OpenCompass to run these.
Yes, OpenCompass for evaluation, and they normalized the scores to make comparisons easier across tasks.
And who are the competitors? What baseline methods did they compare MIG against?
A good range of strong existing methods, simple random selection, of course, but also IFD, ZVP, #instag, DEIT, CAR, and QDIT.
So established techniques.
Exactly. And they mentioned in the appendix they tweaked some parameters for the baselines to ensure a fair fight on the big data sets, which is good practice.
Right. So the moment of truth, the main results. How did MIG stack up?
Pretty darn well. Looking at Table 1 in the paper, across 3 different base models, Llama 3.18b, Mistral 7b v0.3, and Quinn 2.57b, MIG consistently came out on top compared to the baselines on most tasks.
Across the board, knowledge and human preference.
Yes, looking at the average scores for both knowledge-based benchmarks and human preference ones, MIG generally led the pack.
Any particularly striking numbers or findings?
Oh yeah, that Tulu 3 result we mentioned in the summary. Training on just 5% of Tulu 3 selected by MIG gave performance comparable to training on the entire dataset.
Still amazing.
And even more so on the human preference evaluations, that 5% MIG selected data actually led to better results than training on all of Tulu 3.
Better with 95% less data. How?
It suggests the full dataset might have noise or lower quality examples that actually hurt preference alignment, and MIG is effectively filtering that out, selecting only the most impactful stuff. It really underscores the power of smart selection.
Incredible potential for saving compute and time there. Did MIG also shine on the other datasets, OpenHermes and Exota?
It did. Table 2 shows MIG maintaining its lead on those datasets too, suggests it's pretty generalizable.
Okay.
Interestingly, they noted some other methods dipped a bit on Exota. They speculated it might be because those methods' quality metrics perhaps unfairly favored multi-turn chat, which Exota has less of compared to specialized single-turn data like math or code. MIG seemed more robust to that mix.
Interesting potential bias. And they also looked at how performance changes as you give MIG a bigger budget, right?
Yeah.
The data scaling experiments.
Yep, Figure 3 shows that clearly. They tested MIG with different amounts of selected data from Tulu 3, 10K, 20K, 50K, 100K, all the way to the full set.
Yeah.
MIG consistently outperformed the baselines at each budget size. It really drives home the point that MIG gets you close to full dataset performance much, much faster with way fewer samples. Efficiency again.
Okay, so the core method seems really effective. The paper then goes deeper into why it works, analyzing its components. Let's start with that information score function, Vicky. They tested different types.
They did. They compared an exponential function versus a power law function. Figure 4a shows how their derivatives decay, basically how quickly the diminishing returns effect kicks in.
And which worked better?
The power law, specifically feedx to the power of 0.8, gave the best overall results across both human preference and knowledge benchmarks. It seemed to hit the sweet spot for balancing quality and diversity.
Makes sense that the exact shape of that function matters. Yeah. What about the quality metric input? Did it matter how they measured the quality of each data point initially?
Oh, absolutely. They tried using just the number of tags, the IFD score, and the DIT score as the quality input for MIG. Figure 5 shows DIS scores consistently gave the best performance when plugged into MIG.
So using a more sophisticated quality measure like GAIHO helps MIG make even better selections.
Seems so. It suggests DEIT is better at capturing that intrinsic instruction quality compared to simpler metrics.
Got it. Now back to that central component, the label graph. How sensitive is MIG to the specifics of how that graph is built?
Very important question. They looked at 2 key things: the number of nodes, how many unique labels you include, and the edge density, how connected the graph is, controlled by that similarity threshold T.
And what did they find?
Really interesting results in figures 6A and 6B. For both parameters, they saw these sort of unimodal curves, like a hill shape.
Meaning there's a sweet spot?
Exactly. Not too few nodes, not too many, not too sparse, not too dense. Too few labels, you lose granularity. Too many, you might get noise. Same for connections. For Tulu 3, the sweet spot was around 4,500 labels and a similarity threshold of 0.9.
Finding that balance is key. And what about the information propagation itself? Did letting information flow across the graph actually help?
Yes, definitely. Figure 6C shows the impact of varying that propagation weight, alpha. An alpha of 1.0, meaning full propagation according to their formula, gave the best results.
So turning propagation on clearly improved things.
Significantly. It confirms that considering those semantic relationships between labels leads to a more accurate information measure and ultimately better data selection. It's smarter than treating labels in isolation.
It captures the underlying connections. Okay, one last analysis point. They did a grid search for optimal data size and training epochs.
Yeah, it's just a practical check. Table 3 shows they test in different sample sizes, 10K, 20K, 50K, and training epochs 2, 3, 4 on Tulu 3 for both MIG and random selection.
And the best combo was?
For Tulu 3, it looked like 50,000 samples trained for 3 epochs was a good setup for maximizing performance for both methods, although MIG consistently beat random across all those settings, as expected.
Right. Okay, let's wrap this up. If we boil down this deep dive on the MIG paper, what are the main takeaways for people working in this area?
I think there are a few key things. First, they've given us a really novel information theoretic way to measure instruction dataset value, built on this idea of a semantic label graph that captures both quality and diversity.
Right, the core measurement technique.
Second, the MIG algorithm itself. It's an efficient, greedy approach that leverages submodularity to make this smart selection practical.
The how-to.
And third, the results. MIG consistently outperforms strong baselines across diverse setups and crucially shows you can get amazing performance, sometimes even better, with drastically less data like that 5% Tulu 3 finding. The balance of quality and diversity via the graph and propagation really seems to work.
It definitely feels like a step towards more intelligent, less brute force LLM training, focusing on the information content of data rather than just the sheer volume.
Absolutely. It's a very promising direction. This kind of information-guided selection could be huge for making LLM development more efficient and maybe even more effective.
It prompts you to think about what other aspects of data we could model to make selection even smarter.
For sure. And the authors themselves point out limitations in future work, like automating the parameter tuning for MIG or maybe designing custom information score functions for specific needs. There's definitely more to explore here.
Yeah, lots of potential. For anyone listening whose interest is piqued, definitely check out the paper's project page. If available, might have code or more details relevant to your own work.
Good call.
Well, this has been a fascinating look at MIG. Really highlights the cutting edge of data curation for instruction tuning. Thanks for breaking it down.
My pleasure. It's exciting stuff.
Indeed. Make sure you stay tuned for more deep dives into groundbreaking AI research right here.